Our goal is to try and figure out the frictional force and the normal force. This is a relatively easy problem, but it is got a lot of steps. So this is actually not the level of the AP exam. This is still below the level of the AP exam, but there's still a ton of stuff you need to do. So we had already drawn the free body diagram for this, which included weight, which is mg. I'm going to start doing that more and more, just writing mg for weight and not writing a w. It's simply because that's actually common practice. So it's in contact with the ground. So I have a normal force upwards, which I'm not drawing as large as the weight because I also have this tension to the side. And both of these forces are pulling up on the object. And then there's a frictional force backwards. So these are the four forces acting on the object. We know that the net force on the system is equal to 0. So before we go any further, you needed to draw in a coordinate system. And I chose a coordinate system that was aligned with as many forces as possible. It also so happens to be aligned with the direction the system moves, but the system doesn't accelerate, so that's not as big a deal. I know you guys aren't writing that down, but you should have. It's sometimes convenient to have the system aligned with the direction the system moves, but it's more important for it to be aligned with the direction the system accelerates. This system doesn't accelerate. Now this angle was 30 degrees because the tension is not in X or Y. We have to force it to be. And to do that, we need to find a way to get the components of that force. So I had said yesterday to draw a triangle. You're going to wrap a triangle around the angle that you've been given. And it has to be a right triangle. So this part is my right angle, right here. Now, a cursory look at the triangle tells me that this is the hypotenuse, this is the opposite side, and this is the adjacent side. So I'm going to use my trig, and remember that sine of 30 degrees is going to be equal to opposite over hypotenuse. The hypotenuse is the tension. It's the 25 newtons, or the 20 newtons we're pulling with. Cosine of 30 is the adjacent over the tension. Now, I'm doing that because I'm going to need the size of the opposite side, which is t sine 30, and the size of the adjacent side, which is t cosine 30. Any questions about this so far? Well, this might bother a few of you, but I'm going to redraw this because I know I have some students who are going to find this challenging when they do their homework. And I'm just happy to know I have some students who are going to try their homework. I'm going to draw all these forces again, but this time I'm only going to draw the forces as they exist in the x and y direction. So these are unchanged. But then I have this force to the right, which is t cosine theta, and this force upwards, which is t sine theta. This is a reduced free body diagram. And what I mean by reduced is all of the forces are now all the way in the y direction or all the way in the x direction. The reason this is important is we can only do one-dimensional problems. So we have now created two different problems, and each one is one-dimensional. You see, this, Newton's laws, is three-dimensional. We have to break it down into net force in the x direction and net force in the y direction. This will be true for every two-dimensional problem. You'll have to break it down into an x direction and a y direction. We can only do one-dimensional problems. Now, If the net force is 0, both of these will also be 0. We will do one where it's net force equals MA, and that's going to be a little bit more difficult. So it's nice when its net force is 0. Now, this part shouldn't be hard, but some students struggle with it. This says add up all the forces that are in the x direction only. How many forces are in the x direction only? 2. So I'm going to have t cosine theta minus friction equals 0. Any questions? Yes, sir.
Why is it t cosine theta minus friction necessarily, not the other way around?
I chose to the right to be positive.
Oh, right, okay.
That was really only it. It would make no difference. Now we know what t is. It's 20. We know what theta is. It's 30 degrees. So you could figure out what the frictional force is. That's just some math. I want you to do that on your own. 20 cosine 30 degrees. I think it's 1.732. Or 17.32. 17.32. Not so bad? Maybe? I don't know. I think you guys are going to struggle with it. Yep.
How'd you know what unit it was?
The cosine doesn't have a unit. So cosine's unitless. And the 20 was given in newtons.
Oh, okay, sorry.
No worries. So let's do the y. That's where the normal force is. I have two forces upwards. Normal force plus t sine theta. Those are upwards. But then weight is downwards, minus mg. This is going to equal 0. If I want normal, I'm going to isolate it. So I'm going to get mg minus 20 times the sine of 30 degrees. Now, we were given the mass, it was 10, so mg is 100. So I think this comes out to be 90 newtons. Yep. I can't hear you. I don't care. Didn't I say Thursday we're going to do new seats?
Yep.
Yeah, new seats. So, first impressions. This is a two-dimensional problem. I want you to be very, very aware of this.